Section 4.1, Properties of Exponents. Alright, well if you're taking notes, leave a good chunk of space because we're going to have a long list of properties of exponents. We're going to start by letting m and n be counting numbers. Okay, so the counting numbers are 1, 2, 3, 4, 5. So m and n are those kind of numbers, your favorite kind of numbers. They're positive, they're integers, you like those a lot. Okay, our first property of exponents. B to the m is a shorthand notation for writing b times b times b times b, where you have m factors. Alright, so this is nothing earth-shattering. If I give you my base is 4 and my exponent is 3, we use b for base, by the way, you know, I'm sure, that this simply means 4 times 4 times 4, which happens to be 64. Alright, property number 2. B to the m times b to the n. Alright, I'm going to go down here and I'm going to give you an example. This is why I say leave some space. Alright, so if I had, for example, 5 squared times 5 to the 4th. So that's what I mean. My base is the same. My bases are both 5. And my exponents are different. 2 and 4, they might be the same, but in this case they're different. Now, if I ask students what is this, generally about half the class will tell me it should be 5 to the 8th. And half the class will tell me it should be 5 to the 6th. And a small portion might say it should be 25 to the 6th, and a small portion might say 25 to the 8th. Well, here's what it is. 5 squared means to take 5 times 5. On the other hand, 5 to the 4th means to do that. Take 4 of them. So notice what I have. I have 5 multiplied by itself 6 times. That's 5 to the 6th. So notice what happened. The 5 didn't change. The 5 is the base. 5, 5, it's still 5. And notice what happened with the exponents. We added them. Alright, so that's rule number 2. It's b to the m plus n. Okay, so an example of this might look like x cubed times x to the 6th equals x to the 9th. Rule number 3 is pretty similar. B to the m divided by b to the n equals something. Now, first off, for this, we have to have a special little condition that our base cannot be the number 0. Our base cannot be the number 0 because we cannot have 0 on bottom. You can't divide by 0. Alright, well, let's see what happens with that. And we'll do the same sort of trick. I might take 8 to the 6th divided by 8 to the 4th. Well, that means you have a bunch of 8's on top. In fact, you have 6 of them. And then you have some 8's on bottom. And they cancel. So I can cancel that 8 with that 8, that one with that one, and that one with that one, and that one with that one. And notice what I'm left with. I'm left with 2 8's, which I write as 8 squared. Alright, so this shouldn't come as a surprise. When we multiplied, we added our powers. When we divide, 6 minus 4 is 2. We subtract our powers. So this is b to the m minus n. Alright, an example. If I gave you x to the 7th divided by x to the 4th, you would tell me it's x cubed. You just subtract your powers. 7 minus 4. Alright, well this leads to a couple interesting rules. At least I find them interesting. B is a 0. Again, I have to have the little condition b cannot be 0. Let's look what happens. Let's say I gave you 4 squared over 4 squared. Well, I would hope that you would recognize that that's 16 over 16, and anything divided by itself, as long as you're not dealing with the number 0, is the number 1. On the other hand, you could use that division rule for exponents to say this is 4 to the 2 minus 2, which is 4 to the 0. So, since 4 squared over 4 squared has to equal 1, and 4 squared over 4 squared also has to equal 4 to the 0, 4 to the 0 has to be the number 1. And there's really nothing special about the number 4 here. I could have done that with really any base. I could have done it with 12 cubed over 12 cubed, for example. Now, I don't know what 12 cubed is. It's a pretty big number. But I do know if I take 12 cubed and I divide it by 12 cubed, I'm going to get 1. On the other hand, 12 cubed over 12 cubed is 12 to the 3 minus 3, which is 12 to the 0. So that tells me that 12 to the 0 also has to equal 1. So that's rule number 4. Anything raised to the 0 power, except for the number 0, is 1. 0 to the 0 itself is simply undefined. We don't deal with 0 to the 0 for a good reason. Here's my good reason. There are two possible values for 0 to the 0. Okay? And basically, I could argue that 0 to the 0 should be 0, because I could say, well, 0 cubed is 0, 0 squared is 0, 0 to the 1 is 0, so it makes sense that 0 to the 0 should be 0. On the other hand, I could say 3 to the 0 equals 1, 2 to the 0 equals 1, 1 to the 0 equals 1, so it makes sense that 0 to the 0 should be 1. Well, in math, we don't like it when we have two different possible answers. So we don't accept either one of those. So we say 0 to the 0 is undefined. But for any other number, it works out nicely. So, for example, if I gave you negative 6 to the 0, you would tell me that that's 1. You can use negative numbers here too, by the way. Just wanted to throw that in. All right, rule number 5. And again, this one comes from the division rule. If I have a negative power, I'm going to get something interesting. And again, b can't be 0. Okay, so let's look at this one. What if I gave you 5 squared divided by 5 to the 5th? Well, that would be 2 5s on top, 5 5s on bottom. We can reduce. That leaves us with a 1 on top and a 5 cubed on bottom. On the other hand, I can use my division rule and say 5 squared divided by 5 to the 5th is 5 to the 2 minus 5. That's 5 to the negative 3. So, again, what we have here is that 5 to the negative 3 has to be 1 over 5 cubed. And that's our rule number 5. Negative exponents make fractions. A lot of people think negative exponents are going to give you negative answers. Not true. Negative exponents will not give you negative answers. Negative exponents give you fractions. So, for example, 4 to the negative 2 is 1 over 4 squared, which happens to be 1 over 16. Rule number 6, I'm not going to prove this one, just because this is time is starting to add up here. But if you have a negative power and the negative power is already on bottom, the negative power goes to the top. So, in general, I summarize rules 5 and 6 by saying this. Negative powers only switch top and bottom. If you have a negative power and you're on top, you go to the bottom. If you have a negative power and you're already on bottom, you go up to the top. Alright, rule number 7. If I have a times b raised to a power, this is a distributive property. The power goes on both of them. Okay, and this is just easiest to explain by a quick example. If I have 5 x squared. Well, by definition, that means to take 5x times 5x. But then I can switch order. 5 times 5 is 25, so that's 5 squared. And x times x is x squared. So this becomes 5 squared x squared. Rule number 8 is very similar. If I have division with a power, I might not have left myself enough space for all my rules here. The power goes to both of them. And again, we have to have the little rule that b cannot be 0. You can never have 0 on bottom. Alright, I think I have just enough room to squeak in rule number 9 here. And this is going to be my last one. If I have a base to a power and then another power, we multiply our powers. And I'll give you an example of that one in just a second here. But there's a list of all of our rules. This concludes the first half of the video for this section. The second half of the video, I will work through a bunch of examples to show you how you're going to use these rules and give you some homework problems.